Welcome to this week's ITS weekly seminar. It's a great pleasure to, there are seats here. Yeah. It's a great pleasure to introduce today's speaker, Professor Johannes Royset from University of Southern California in the Department of Systems and Industry and System Engineering Department. Johannes has many awards, received many awards. You probably read his bio. He has been serving either as a past editor or associate editor on almost all the top journals in the operations research field. So I would not spend time on that information. You can just read his bio. He's a leading scholar in risk quantification, stochastic optimization, and so on. Contributed a lot to the ideas, fundamental ideas and methods in these areas. Now, what I can mention based on my own experience is, besides all those wonderful things that you can read from a typical bio, he is also a very, very curious individual, a thinker, and he has a genuine interest in real engineering problems. And so, for example, a few years ago, when I reached out to Johannes and telling him, here's a problem I'm interested in, we have observations from various locations on traffic flow and so on, but those are localized measures or spread it over network. And we want to infer what is the global travel demand from locations to locations, which cannot be easily observable. And it's a high dimensional problem. And then because of the variability, uncertainty, we're not just happy with a point estimation of the demand. So it's high dimensional statistics and so on. Right, so and Johannes contributed ideas how to, how we might pursue this, and how we might design efficient computational methods to deal with the high dimensional statistics and so on. So that's just one example. He has collaborated with engineers in different domains. I thought many of us are interested in climate resilience, all sorts of uncertainty related topics. So it would be great to have some exposure, whether you are more analytical or less analytical, doesn't matter. It would be nice to be exposed to some of the concepts and the measures that Johannes will share with us related to uncertainty. Let's welcome Professor Johannes Royset.
Okay, thank you very much. Thank you for the nice introduction. Always enjoy coming to Davis. A lot of good memories and collaborators here. So I'm going to talk a little bit about risk today. And, as you imagine, risk comes up in many, walks of life. Many areas of engineering is heavily affected by risk in one way or another. And I want to try to talk a little bit about kind of general principles that we can use to address risk, whatever application that you might have in mind. Hopefully we can make some connections with what your particular concerns are. So talk a little bit first, very briefly, of some examples, for instance, from maritime transportation. I'm originally from Norway, has a very long coast, and of course one thing that they're worried about in Norway are ships running aground. And you have heard about Exxon Valdez. This is the so-called Gullfoss incident near Hvaler, not too far from Oslo in 2011. So there could be many small or larger incidents, which is of course troubling. There could be pollution, oil coming out in the water and things like that. So the question, for instance, that we were asked at one point is, how can you position rescue tugboats to try to reduce the chances of incidents like this? And then naturally risk will come up. How should we value or quantify risk in such a setting? Another area where risk comes up is in modern machine learning. there, we know we have some data. We're going to try to make some predictions of some kind, and there are risks of making errors in various kinds. And look at this classical problem, which goes back to how the US Postal Service tried to find a way of automatically read zip codes on letters. They looked at this so-called MNIST data set, and what we quickly figure out, or the machine learning community quickly figure out, was that it is possible to train a machine learning algorithm to recognize handwritten numbers, particularly when the data set is clean, meaning that there's no error or any mislabeling. Because if you have mislabeling, for instance, there could be a number 7 here that's been labeled as 2, and a number 0 that was labeled as 6, and other types of mistakes in your data set, then things becomes much more difficult. And you can think about what type of risk you're facing in such a situation. Of course, this is a very simple case, but with many much more complicated machine learning tasks, you will have various ways of risk that come in on making mistakes, in particular, say in safety issues, self-driving cars and things like that. We'll be worried about a machine learning algorithm making some sort of mistake, and it could be big risks associated with that. How should we handle a situation that? How should we think about risk in situations like that? Okay, so in this talk, I'm going to try to talk about 4 things, and feel free to interrupt, and I'd like to have a little bit of discussion if you have any comments as we go along. I'll continue a little bit about the maritime transportation application as a sort of an introduction to the concept of risk. Then we want to talk a little bit more generally about uncertainty and decision making. What are the challenges? Can we just move, take the most natural thing, maybe talk about mean and standard deviations? And what are the problems and challenges associated with making decisions under uncertainty? And then the main thing I'm going to try to convey to you today is that measures of risk are actually a very useful tool. And measures of risk are more than just ways of measuring risk. It's actually a mathematical framework to think about risk that turns out to be very computationally convenient, turns out to be axiomatically consistent and kind of valid in some sense. And I'm going to end with how we can use these concepts in various statistics and machine learning setting, particularly when we are worried about making big mistakes. Maybe we are not entirely satisfied of having good performance on average, but we're worried about maybe something in the worst case, or something more conservative or risk averse, which is ways how we can handle things like that. So that would be the end. Okay. So let's go back to that maritime transportation setting. So a few years back, 5-6 years back, we were asked to consider the following situation. This is before the war in Ukraine and everything. So Russia were sending a lot of oil tankers. This is the northern part of Norway. You see here, if you think about the map, this is the very top of the map of the world. And Russian oil tankers were coming across here and going down the North Sea and into the Atlantic for various places. Anyways, these can be oil tankers or other types of ships, but we were worried about, if any of these vessels lose power at one point or another and start drifting towards land. Okay. So this was a real concern, and it's a real concern not only in Norway, but other places. So the question is, how can we position tugboats? Maybe there's a tugboat here. How can this tugboat be in a good position to respond to these possibilities? And we don't know when these type of events will happen. What are the risks associated with this? So the first thing that faces us, how should we quantify risk in this type of settings? And the first thing that came to our mind was to consider risk as simply the cost of grounding, $10 million or whatever it was going to cost us to clean up that beach, times the probability of that event. So this is maybe the simplest way we can think about risk, is if you have this type of Bernoulli event, it happens or it does not. And if it happens, it costs me so many $1 million, and if it doesn't happen, it maybe cost me nothing. So this could be one way we can quantify risk, and it could be a starting point. And this kind of served us well. And when I say served us well, it's because it was easy to explain, and that's something that I think is important. You want to have something that can be easy to explain to a decision maker, somebody that is not necessarily very mathematically inclined. And it should also be something that we can work with computationally. And that's something we keep on going to talk about today, is how we can make sure that we make choices about how to quantify risk that is computationally attractive. So eventually, when this is fed into other things, other models, etc., we are able to actually compute, or we don't make life hard for ourselves. Okay, so with this particular choice of risk in this case, we were able to do some modeling, and there was of course a discretization of the ocean. This is the piece of ocean that we saw on the earlier map, and these trajectories are possible scenarios. Maybe the vessel starts drifting here and follows this particular trajectory, or maybe start drifting here, follow this trajectory. So there's a sense of uncertainty. So we had to quantify uncertainty, of course. And then we had to figure out a few other things. For instance, what are conditional probability of being able for a particular tugboat to hook up with the vessel coming drifting. So there's certain things that we have to be modeling. But all of this can be put together in an optimization model, a mixed integer nonlinear program. There's some sort of a quantity here that we'll be caring about. Remember, we're interested in the probability of this event happening. And we can actually find out a formula for that. We had good linear approximations. And we were able to put this into a modeling language called Pyomo, and we'll be able to, solve what we thought were realistic instances, planning, looking 20 hours into the future, certain discretization of the ocean, so many cells, etc., etc. And we're able to solve and optimize what was the right, best, or optimal place to put these tugboats, in this case, 2 tugboats along the coast. And we saw it in different case studies. For instance, there was an incident in 2014 where a ship actually ran aground. And we kind of will replay that incident and saw how, if we had just been on the spot that day, we could have guided the tugboats a little bit differently than that would happen in actuality. And we could have guided the tugboat to come along like this, and we could have saved so many millions in some sense. But the important takeaway from all of this is that by choosing a particular way of quantifying risk, we were able to do something that was computationally attractive. We'll be able to compute these things to find the optimal trajectories in a few minutes. So something that a decision maker can doesn't forget the answer forget the question before you get the answer type of situation. And we were able to adopt a relatively simple concept, probability of the event, time to cost of the event, that we can explain to, in this case, the Norwegian Coastal Administration. Okay. But how can we think about this? Well, very specific is. How can we think about this more generally? So before we get into details about measures of risk, let's talk a little bit about uncertainty conceptually. And maybe we can start with this picture that maybe the first thing you see in Stat 101, you see this bell curve. And somehow you're being told to look at mean values and standard deviation. My son in 6th grade, this is the first thing you learn in statistics, so like data class is the mean and standard deviation. And that somehow is getting ingrained in our brain, and maybe sometimes it becomes difficult to move away from this. But what is the trouble with focusing too much on mean and standard deviation? Well, if we look at actual data, from various experiments, real-world situations, and for instance, this is one, again, somehow, I'm in the maritime domain, is this type of high speed. I don't know if you've seen that, particularly in the Mediterranean. There's a lot of ferries, or this type of high-speed ferries, where you just have a hydrofoil in the water, you're kind of flying above the water. So this is one way of building high-speed passenger ferries. So we looked at a study like that some years back. And one of the things we looked at, for instance, those hydrofoils, like wings of a boat, they stick into the water here, but they, of course, will be bending. There will be a bit of a weight on them. They are lifting up the whole vessel. So what is the displacement of those hydrofoils? And here you see a probability distribution of various types of simulations we did. And what we see that this picture is nothing like what we saw here. So this is not a surprise. Real data, real world data typically does not follow the normal distribution in many situations. Of course, sometimes it does, but often it does not. So that is one thing. So often we also have a particular concern about one tail, meaning that in this case, we talk about displacement, how much this thing bends. Well, I would probably be more worried about how much it bends than how little it bends, meaning that I would be more concerned about the right tail than the left tail. So in many decision-making situations, we are not really in a symmetric setting, but we're more focused on or concerned about one part of that picture. So that is something that we should account for in some fashion. Let's talk about a very, very special situation with two triangular distribution. So play along if you like. I'm going to make two decisions. We're going to make a choice between decision number 1 and decision number 2. Okay. Decision number 1 has some sort of uncertain response, a random variable z1, and the other one is z2. And they have this probability distribution. We can look at z1. Z1 has a triangular probability distribution, and the support is from -1 to 1. So this is the situation for that one, and similarly for blue. And I can ask you, which of the situation would you prefer? Would you prefer to have the random variable z1 or z2? Okay. Well, I guess that depends a little bit on which tail you're worried about. And why don't we, for the sake of this talk, always be concerned about the upper tail. So what's happening on the right tail there, it's what's concerning. So we talk about displacement, high values are bad. We talk about travel time, high travel times are bad. Cost, high cost are bad. So everything that's high is bad. So we're worried about what's happening on the upper tail here. So if that is the setting we are in, would you prefer to be faced with the blue or red distribution? So this has to do a bit with preference. That's something we can have a long discussion. Some of you might more like to go to Las Vegas and a bit of a gambler. Other ones are more concerned, and risk averse. So of course, with personal preference and depending on the setting, things can vary. But for instance, if you say, hey, I learned in Stat 101 mean and standard deviation. So we can compute the mean and standard deviation on these two distributions. I can see some of you already trying to do that maybe on your computer or something, but imagine we compute the mean and standard deviation on these two distributions. What we get, actually they have the same mean and the same standard deviation. So if you only learn about means and standard deviation, that's the only thing that you base all your life on is mean and standard deviation, you'll be indifferent between these situations. But I would say that would be maybe not the right thing to do, because if I'm worried about the upper tail, the red one looks a bit less pleasant, because the red one, I can get rather high values all the way up to 1, while the blue one, I'm guaranteed to not get anything worse than 0.33. But mean and standard deviation does not reveal this difference between these two. But let's look at something that is maybe even more troubling. Okay. Imagine again we have two situations. We have a random variable E1 and E2. Maybe these are some sort of uncertain errors. I have a predictive model, two predictive models. One has certain flaws, another one has maybe certain other flaws. Yeah, one has error E1 and other has error E2. These errors are random. Okay, they are random, but how are they random? Well, let me tell you. There are two possible outcomes. I'm going to roll a die, 50-50. Okay, so I guess I'm not rolling, I'm going to flip a coin, I guess. I'm going to flip a coin, 50-50. Okay. If I get head on my coin, for instance, the first random variable has value 0, and the other one is 1. So since we talked about errors, I guess error 0 sounds pretty good to me. So that's perfect. And this other one has error 1. That's a bit of an error. So I guess this was when I flipped the coin, I got head. If I flip and get tail, then the first random variable has value 2 and the second random variable value 2 as well. So then they are the same. Both have a bit of an error. Okay. Okay, so that's all good. But if I now say, which of the two predictive models should I use? Well, 50% chance they're going to be equally bad or equally good. And with 50% chance, the number 1 will be better. So I guess everybody would say that the model number 1 is the one to choose. No, I mean, everybody can agree on that. I think that model number 1 is the better one, equal to same or better than the other one. But here is again a little bit of trouble. Imagine that if I do the ranking between these two models by computing their mean plus 2 standard deviations. Computing the mean, I can compute the mean of these things. What is the mean of this guy? I guess it's a 1, isn't it? And the mean of this guy is 1.5. So I can compute the mean. I can compute the standard deviation also. So if I say, well, I like low means, I like low standard deviation. Sounds like mean plus 2 standard deviation could be a criteria for me to do this ranking between these two guys. But here's a bit of a trouble. The trouble is that the first guy has a rather big standard deviation. So this number actually becomes kind of big. So if I use this ranking, it is predicting model number 2 that wins. The one that we all agreed was worse. So that's a paradox. There's a paradox that if I do a ranking between the models using mean and standard deviation, I'm basically misled badly, because I'm picking as better the one that is obviously worse.
So what happens if you use the higher order moments?
Higher order model,
Do they contribute to anything, or they don't really?
I think higher order moments will also be bad for this first guy, because there's, you know, particularly
They're non-continuous. They're non-continuous distribution.
Right.
But I can compute fourth order moment if you want. Fourth order moment is going to be pretty high.
I'm trying to see if just getting moments by themselves are a wrong measure to use in this problem, right?
No, but the problem is the second one is more concentrated, right?
Sure.
You would think concentrated is better, but it's concentrated actually on the worst.
Exactly. So this is, we often thought that little uncertainty is good and big uncertainty is bad, but it is more complicated because standard deviation is a symmetric thing. So we're measuring deviation on the upside, on the downside equally. But I think in this setting, we don't want that because we are worried about one side more than the other. So have a symmetric measure of variability is the wrong one. So whether it's the standard deviation or the fourth moment or sixth moment or something, all those will be symmetric. So it will not be the right thing to do. Okay. So this was a lot of trouble. So what can we do to get out of all of this troubling situation? And this is where I'm going to be proposing these measures of risk. Okay. So what is a risk measure? So if you want to take with you one definition, there's this line here. A risk measure is a mapping from a random variable into a number. It's nothing more, nothing less. So imagine that I have some sort of distribution, which we can think of as a representation of the random variable, at least for this discussion. And I take that, distribution, and I somehow produces a number from it. Of course, the expectation would be one example of a risk measure according to this definition, but it could be many other ones. What do I want this risk measure to somehow accomplish for me? I certainly like to avoid embarrassing paradoxes, one we just faced on the previous slide. We don't want to be a situation where we recommend something over something else, so in a way that is obviously wrong, like the mean plus standard deviation. So we want to avoid this type of embarrassing paradoxes. We want to promote robustness and conservativeness. So we are often in a situation where we are worried about what's happening out in one tail. So somehow we would like to try to characterize that in some way. So maybe having just expected value will not be entirely satisfactory because it doesn't really capture what's happening in that maybe worrisome tail. Another thing that you might want to be concerned about is to capture decision makers' preferences in some way. These can be very complicated, and maybe we talk a little bit more about that later, but at least in some way we want to be able to respond to somebody that's more risk averse to somebody that's less risk averse. So we want to have a little bit of tuning opportunities if we need to. Then something that I would like to stress, and I mentioned earlier, we want to have something simple. And you probably want to stand in front of an executive and explain this the way we decide to do this was in this and that way. If you need 5 slides and explain all the math, maybe you're already losing your audience, right? So you want to have something that is intuitive, that can be understood, maybe by the public. Maybe this is going to end up on front page of New York Times, and you have to be able to justify it in some way. And then one thing I also mentioned earlier was computable, because the fact that the way you're quantifying risk is not going to be necessarily the end of it. That's going to go into a bigger process of analysis and computations. Maybe you're going to use some optimization. Maybe this is going to form an objective function, as we had that maritime transportation example. Our risk became our objective function to be minimized. So it does that somehow causes a lot of headache computationally. It does make a very nice problem or a very ugly one, a non-convex optimization problem, or whatever it might be. Or it might be fed into some sort of learning process. We talked about machine learning a little bit. Maybe we would like to become somewhat the loss or the objective of a training procedure, and we want to make sure that this is computable as much as possible. Okay, so these are the things we are hoping for. So what could be a potential risk measure? And I want to throw you one here now that I think is maybe the most important one from my point of view, and then we can see what you think. This is what we call super quantiles. So what is a super quantile? So I imagine I have a random variable z. It could be normal distribution, could be a Bernoulli distribution, it could be any distribution you can imagine, doesn't matter. Some distribution has a random variable. Okay, the super quantile at some level alpha. What is alpha? It is some sort of probability level. This is something that we can adjust to capture various things. Okay, so I have an alpha. The super quantile at the random variable is then going to be the average of 1 minus alpha% of the worst outcomes of the Z. Well, that's a little bit to think about, but maybe a picture can help us. So remember, I like those triangular distributions. So here's a triangular distribution again. And remember, we're supposed to pick an alpha. Maybe I pick alpha equal to 0.7. Okay, I pick alpha equal to 0.7. 0.7, I'm supposed to take 1 minus, so I guess that makes it 0.3. I'm going to take average of the 0.3% worst outcomes. So I'm up here in this upper tail. Keep in mind, worst for me is in the upper tail, on that right tail. Okay, so that's what's worst for me. So I'm going to take the average of those worst 30% of the outcomes. That's the super quantile, and alpha equal to 0.7. Okay. Of course, now the question is, what if alpha changes? Well, for instance, what if I take alpha equal to 0? Then it's average of 1 minus 0 worst outcomes. That meaning average over all the outcomes. So I'm just back at the good old mean value. So I'm capturing, if you like mean values, that's part of the story here. If I pick alpha equal to 1, then I'm really pushing my luck and pushing out on that tail on the right side there and go out to the very worst possible value, which in this case would be 1. So for me, I can adjust now alpha between 0 and 1 and get a whole range of super quantiles. Which one you would like to use in a particular setting, depending on how risk averse, how much focus you want to be on the tail versus the average. So you can slide between that in a manner that can be explained to a decision maker. You can say, hey, I'm planning for the worst 10% outcomes that might come our way. That's something that you can say to the governor, and hopefully you will track. So these super quantiles came out originally of financial engineering, and of course also by name conditional valued risk, average valued risk, and the expected shortfall, the other things you find if you go in Wikipedia. Okay. Remember these triangles we talked about earlier? This was the triangles that if I compute the mean and standard deviation, I got exactly the same, and somehow realize that I'm missing out on something, or I'm not really identifying that they are different. I only look at mean and standard deviations. So if I now bring in super quantiles, and maybe I look at the average or the worst 10%, remember that corresponds to picking alpha 0.9. So I'm picking alpha 0.9 after 10% worse outcomes. So where were we? We average on the 10% worse outcomes, and I worked at hard, I compute this for you. The worst or the 10% worse in the red case is somewhere here, in the blue case is somewhere there, and I even computed two numbers here. And I see that the blue one looks better. So on average, in the worst 10% of the cases, I'm up at 0.28. So this is 0.28. So that's better than this point here, which is 0.58. So by looking at these super quantiles, I was able to indeed identify that the red is more troubling than the blue. Something that the standard deviation couldn't highlight for us. And of course, these super quantiles are one-sided. They focus on the average on that tail out there, and really somewhat ignores what's happening in the other tail. And that might be exactly what you want in a decision-making process. This asymmetric situation can be captured. Okay, so what are the good things that can come from these super quantiles? Well, I'm not going to go through all the examples, but at least you might take my word for that these paradoxes that we had, for instance, associated with standard deviation, they will go away. And we can show in a very rigorous mathematical way that you avoid all the paradoxes that people worry about in some specific sense. So at least you can rest assured that if you do a super quantile as your objective function, whatever you're doing with it, you're not going to embarrass yourself in the same way that you could with a standard deviation. I can adjust conservativeness. That was how I pick alpha. I can adjust alpha depending on, you can have a discussion with your boss to say, hey, how conservative you want to be? And you can respond very easily by adjusting this alpha, how far out in the tail you want to go. It's relatively simple. I think you can explain it to the governors we talked about. It turns out there's something more fundamental about it. It is actually all reasonable risk measure in a mathematically, formal, like axiomatic manner can be built up from such super quantile by averaging them and other processes. So it's some sort of a fundamental building block of even more general risk measures. They are computable in some sense. I guess that's something that maybe not entirely clear at this point. I said the super quantile was the average of what's going on in the tail, how easy it's to compute it. Well, that might be a little bit, unclear at this point, but I'm going to provide evidence that is computable. So it's something we put in the optimization and learning algorithms reasonably easily. And there's some important connection with ambiguity. And it's something that we shouldn't completely forget, although here I'm somewhat seem to be saying, hey, I have a random variable, it has a distribution, and kind of that's my starting point. But in reality, where did that distribution come from? That's of course just as an important question. There might be ambiguity about this distribution. Maybe because we don't have enough data, or maybe this is something maybe conceptual that's never been observed. There's some sort of subjective situation that you're trying to model something. So there's often, or not to say almost often, or all the time, we have some ambiguity about our uncertainty model. It turns out, and I'll highlight that a little bit more later, that these super quantile risk measures somewhat implicitly hedge against this type of ambiguity, helps us to even counter ambiguity in some specific way. Okay, so here's some big formula. If anyone like big formulas, here we have one. I just felt that I can't come so far without giving you any formulas. There is one formula, in fact there are 4 of them, because I wanted to show you that a super quantile for a random variable C can be computed in different ways. And we can talk a little bit about how these different ways can be implemented in different algorithms. I guess sometimes I use Q bar for just super quantile. So let's say Q bar I mean super quantile. The reason I like this little bar, because bar, think about averaging it out. And Q, think about Q as a quantile. And you know what a quantile is? You know the median is an example of the 50% quantile, and the other quantile. So the quantile is called Q here, and this is kind of average beyond the quantile, which is, I guess, a more formal way of defining this. And that's what's said here. So super quantile is the quantile plus what's beyond average of it, right? And that's what it's kind of said in words earlier. But here's the more formal mathematical definition of it. That's all good, but it doesn't really help us too much with computations. But here's a major breakthrough that came at the turn of the century by two famous mathematicians, Rockefeller and Royset. And they came up with this formula that I call the Rockefeller-Royset formula for super quantiles. And it was really a major breakthrough because this is something that we can now use computationally. It might not be apparent immediately because it looks still like a rather large formula. So it may be still a little bit hard, apparently. But the good news is that if I want to minimize some sort of super quantile, the fact that I have another minimization going on here is just more of the same. If I was minimizing something and now I have to minimize a little bit more, actually a little minimization there is piece of cake. And then I have some formula. These are just kind of given numbers. And then I have expectation. And expectation we're pretty good at handling. You know, you learn it in step 101. We know that many optimization algorithms, learning algorithms have been dealt with handling expectations. You know, for instance, in machine learning, you're averaging across your data points. So we're pretty good, you know, stochastic gradient descent at the different methods one can use to minimize expected values. So the key thing about this Rockefeller-Royset formula, that super quantile minimization becomes just as easy as minimizing any other good old expectation. So that is the reason why I claimed earlier that super quantiles are computationally attractive. I'm waving my hands a little bit here, but you can see at least we can get back to an expectation. There are other formulas, for instance, like averaging or quantiles, which might have interesting interpretations, but let's leave that aside and go to the one on the bottom here. This is the one that has to do with the ambiguity that I mentioned a little bit earlier. So this basically says that a super quantile can be interpreted as a worst case expectation. So that means it says that if I am a guy that likes to minimize a super quantile, that is exactly the same, according to this formula, as being a guy that wants to minimize an expectation, except I'm going to take the worst case expectation. Okay. So if I'm a little bit unsure about my probability distribution, one way to handle it is to look at a worst case distribution. And that is somehow built into this formula. That here we're looking at the worst case distribution within a certain range, of course not worst universally, but worst within a certain ball in some sense. So that means that super quantiles are somehow automatically what we call distributionally robust in some sense. Okay, so that was my formula slide. So we might step back for a moment and say, hey, you know, people are making decisions under uncertainties for decades. And you might remember when Neumann and Morgenstern wrote a very famous and influential paper about expected utility. Was it 1943 or something like that? And of course, much has been said about utility theory. Where does utility theory fit into all of this? I don't seem to have mentioned yet. Well, it turns out utility theory, which are the much elegant mathematics about that, nice axioms and things like that, it's been increasingly criticized among economists. For instance, there are 4 economists here that wrote this nice thin book. I recommend it if you have, you know, want to do something over the long weekend. It's a good book to read called Risky Curves. It talks a little about the problem with using utility theory in practice. In particular, often there's a tendency to pick very complicated utility functions, which really is the wrong way to move according to them. They're advocating more for simpler concepts and say maybe, you know, they call it the empirical failure of respective utility, that there's some issues with that. And I'm going to show you a concrete example how risk measures are completely different than utility theory in a moment. Another is, of course, reliability theory. If you somehow, are familiar with, being in system reliability, what's the probability that a network will be connected from one node to another? Well, the nodes can be, or the arcs can be failing, and things like what's the probability that the whole system is connected? There's a long history of reliability theory, of course, and that's all good. But it turns out this type of focus on probability of failure is also a little bit problematic from my point of view. And the main complaint I have about that is a little bit black and white. That failure, not failure, which sometimes, but not always, represent what we have in reality. The other thing that is problematic with probability of failure is computability. It's typically very difficult to compute failure probabilities. I'll show you an example of why that is problematic. And risk measures, in particular super quantiles, can be more convenient. Okay, so I promised you a little bit about utility theory, so here it comes. So I'm going to again give you a couple of simple cases. I have two random variables, Z1 and Z2. This time they're uniformly distributed. So think about this, some sort of cost you're facing. One way or another, you're facing these costs, and you wonder which one, would you prefer somehow. Okay, maybe you, in your, great wisdom, trying to figure out which one of the two random variables to adopt, you compute the expected values. And I can see, obviously, if I compute the expected value of these two random variables, to figure that Z2 is better. It has a lower expected cost. So maybe that's what you're going for. Maybe that's one way to make an assessment. Another possibility, and you said, utility, we brought up, what about utility? Well, a small side thing about utility. Utility was developed by economists, and economists like to make money, it seems like. So they like big numbers. I'm an engineer. I like low numbers. Keep in mind, I said that the right side was bad and the left side was good. So I'm going to focus on minimization. Left is good. So I'm going to not talk about utility, but I'm going to talk about disutility. Okay, so it's a negative or utility function. Okay, but that's a minor switch in orientation. Okay, so imagine that I pick up the following utility or disutility function, if you like, which is piecewise linear. It's like a hinge. Okay, piecewise linear utility, a relatively simple utility function, and it kind of has a certain slope. Okay, suppose that's what I have. So I can now try to say, based on this utility function, let's make an assessment. Should I go for Z1 or Z2? Okay, I can compute the utility, expected utility in each of the cases. It turns out 1/5. Same, both cases. Okay. So if I'm based on my, my decision on this utility function, I would say I'm indifferent between these two costs. Okay, so here is another and a third way we can try to make a choice between these two random variables. Let's imagine that we have an opportunity to put an investment, $50 in the bank, gamma dollars in the bank. If I put this $50 in the bank today, I will be in a bit better position to face this cost, whichever one it is I'm decided to face. I will be in a better position to face these costs, right? Because I have $50 already in the bank that I can pull out and mitigate that big cost. So my future displeasure, according to my utility function, will now not be Z that goes in here as we have here, but Z minus gamma, because I take those $50 out of the bank and put them towards my Z that I'm facing. So my utility now, or displeasure or disutility, if you like, is going to be this number. But of course, those $50 came out of my pocket today, so I should account for that as well. So really what I should figure out, if I'm going to make my decision now, I'm going to look at this, displeasure in the future, accounting for how much money I put in the bank, plus the amount of money I put in the bank. So I put $50 in the bank first, which of course is a bit painful for me, plus the pain that I will face down the road when the Z comes my way. Fortunately, when Z comes my way, I have those $50 that I use to offset. So now the question is, I said $50, but really what we should do, we should be minimizing this quantity by finding the best gamma. And for those that have, good memory, you might remember my big formula slide 5 minutes ago. The big formula slide had a formula that I call the Rockefeller-Royset formula, and that looks like this. So this is actually the super quantile of Zi. So it turns out that if I follow this thought, that I'm going to kind of try to mitigate my risk by putting $50 in the bank or whatever optimized amount I will put in the bank, that is just the same thing as computing the super quantile. If I do this numerically, say with a super quantile at level alpha, so I'm looking at the worst 20% of the scenarios in my earlier discussion, I can compute this super quantile value, 3/4 for Z and 1 for Z2, so Z1 is better. Why is Z1 better from a super quantile point of view? Well, we can look up. Here is only a uniform distribution going up to 1, but this guy has a uniform distribution going all the way up to 2. So this has a more unpleasant tail. Z2 has a more unpleasant tail. It goes further to the right, and that's what we're worried about. This is a cost after all, and that is reflected when we compute the super quantiles. But maybe the discussion here is that looking at the super quantiles has this interpretation of going through a process of trying to mitigate risk by putting $50 in the bank that will be available to offset your displeasure when the rainy day hits. And that's a fundamental different process than the utility. Keep in mind, I use the same disutility function here as here. But in the risk measure, the super quantile business, I somehow was thinking about not only what is my displeasure about this random variable, but what can I do about it? I can put $50 in the bank, I can put $100 in. If I have this possibility of mitigating, which of the two Z's are more pleasant? They were equally unpleasant here, but when I look at mitigation strategy, one is easier to mitigate than the other, and that's important. Maybe the two random variables are equally unpleasant, but one can be mitigated more easily, and that is built into the super quantile formula. Okay. I was kind of putting down failure probabilities. I put up this book by Marvin Rausan. I took a class from Marvin Rausan many years ago in Norway, so I hope he doesn't listen to this recording, but it was a very nice class. But anyways, I said failure probability was not a good way. Why did I say failure probability has some issues? Well, it was too black and white, I said. Failure, not failure, and life is not always like that. But I said there was also another thing that was worried. That was that failure probability is computationally very difficult. And see if I can convince you why that is difficult. But before I get to that, I need to try to convince you that a failure probability or making a decision based on failure probabilities is the same thing as making a decision based on quantiles. Because what is a quantile? Quantile is really about how far up do I have to go to get to a particular probability level. So I'm really looking at, there's certain probability mass to the left and the right of the quantile, right? So that's roughly the same. It's kind of like an inverse statement of having a failure probability being above or below a certain level. So if you don't track 100% that's okay, but just take it as maybe as face value that if I'm in a situation, as I talk about failure probabilities, that's equivalent to being in a situation where we want to make decisions based on quantiles. Okay. And I know how to do quantiles, say the 50% quantile, the median, I could compute the median. So if I give you two random variables and I say, hey, these two random variables, I'm going to prefer one to another, I can compute the mean and see which one has the better median, and see which one has the better median. I can certainly do that. Okay, so let's compare quantiles versus super quantiles. And quantiles, I say, maybe more computationally troublesome versus super quantiles. And let's look at a very simple case here. Imagine you have two random variables, Z1 and Z2. Let's see what's happening with these two random variables. Z1, I'm going to value 2. By the way, these are some sort of, payoffs or costs or something like that. They're going to happen with probability 0.1, and C1 has -1 probability 0.9. And Z2 is exactly the same. But these two random variables are independent. Okay, so now I have to make a decision. I'm going to, I'm lucky I have $1 million. I'm going to put $1 million into one of these two random variables in the following sense, that I'm going to look at, going to put my $1 million X into the first random or first instrument and the rest into the second. So if I put all my money into the Z1, so X is 1, so then this goes away. So then what I'm facing as a loss is simply Z1. And I can look at that, it sounds like, my, 90% chance I get -1, so I get $1 million back. Or unfortunately, with 10% chance, I have to pay $2 million. And I can flip this around, put all my money in the Z2, that is just a symmetric situation. But then I can maybe do a balance between the two. $500,000, $500,000. What would you do? Well, one thing you could do is say, let's compute a quantile for every possible X. And I did that. I computed quantile. Here's the quantile. There's the quantile. And I look like I put alpha equal to 0.9. So it's 0.9 quantile. So this is, I'm plotting the quantile for every single X. So based on this, it looks like the lowest value, the best value is either X equal to 0 or X equal to 1. That means that the best thing turns out to be equally good if I look at quantiles is to put all my eggs in one basket, my whole million in one of the instruments, or the whole million in the other one. If I look at quantiles, this is what I'll be guided to do. The worst thing to do according to the quantiles would be to split 50-50. But who of you are playing a little bit with the investments and stuff like that? If you want to invest, we have something called hedging, right? Which is a useful tool to help offset losses. And what the quantiles is saying here is that don't hedge. It completely misses the opportunity of hedging. Super quantiles, on the other hand, I can compute the super quantiles. That's the Q bar here. I compute the super quantiles for every X, and I get this V. What is the minimum in this case? Is X equal to 0.5. I should balance my investment. Hedging. So super quantiles promotes hedging. Quantiles does not. But there's something more. If you take an optimization course, there's a magical word in every optimization course called convexity. Convexity is that the function looks like this, which is easy to minimize. Concavity looks like that, and that's hard to minimize. So it turns out, and it goes to the computational side, to minimize a super quantile is a convex optimization problem very generally. While minimizing a quantile is typically not. So if you're looking at what is computationally more attractive, super quantile is much superior to quantiles, and by association, failure probabilities. Okay, how many minutes? 10 more minutes or 5 more minutes?
Yeah, maybe 7 to 8 more minutes.
7 minutes.
Yeah.
Okay, so I talked a lot about super quantiles, and they are the building blocks of many other things. And in fact, there's a bigger picture here that I'm not really telling you about. There's a whole, what we call a quadrangle, where super quantile risk is just one corner, and it could be many other measures of risk up here. They can be connected to regret, deviation, of which standard deviation, which I put down earlier, is among those over here, but there could be other options too. And various measures of error. These are all connected in various ways, and there's nice theory around it, referring here to theorems in our book, but this is originally due to Rockefeller and Royset as well. So it turns out that this quadrangle gives us many opportunities to transfer these ideas about risk over to a statistical setting. So let's talk about that the last 5 minutes. So what is statistical learning? Statistical learning is, at least from a high level, is simply that we're trying to train some parameters. Imagine a vector W parameters. That we try to optimize some fashion such that a predictive model that they call FW somehow matches the data. This is, of course, what we call supervised learning. So how do I say I matches the data? Well, I have some X and Y data. If I put my X into my predictive model, I better reproduce Y. Think about regression as a special case. Of course, it could be many other things. So what is typically done, classically, as you learn from statistics 101, is that you're going to take the average across your data using some sort of loss. Least squares come to mind. And of course, behind least square regression, but it could be other, it could be quantile regression, or it could be other losses, entropy loss, or whatever it might be that you adopt in here as L. But this average, of course, is just an expectation. So what you learn in statistic 101 was to minimize the average loss. But what we talked about in this talk was, of course, that there are not only averages out there that we use to try to make decision. In this case, we're making a decision. What's a good statistical model? What's a bad statistical model? That's our decision at this point. But we don't have to use an average loss. We can do other risk measures. For instance, we can put in a super quantile here, where you can adjust alpha. If you take alpha equal to 0, you're back to the expectation, by the way. But you can put other alphas, which put more focus on the big losses. Maybe you're really worried about having a statistical model that has some sort of very outlier, some big losses somewhere across your data set. Then you might use a risk measure. And we know what that has an interpretation, average or the worst 10% losses. But what we saw through that Rockefeller-Royset formula is that actually a super quantile might at first look kind of intimidating. Thanks to that Rockefeller-Royset formula, I said it got us back to an expectation. So if you love PyTorch or something like that, and you really like to use stochastic gradient descent, actually you can minimize super quantiles just by using the machine that's existing for expectation minimization, like stochastic gradient descent, because thanks to this formula, every super quantile can be written as an expectation. There's also an other interpretation, and for those of you that are interested in robust or adversarial machine learning, we know that many work in machine learning are focusing on what happens if your data somehow is changed or something that is attacked in some way. Well, we talked about a super quantile risk measure had that automatically built in. There was the formula slide on the bottom. There was what I call about the ambiguity case. And it turns out a super quantile can be interpreted at the worst case average loss. Worst case over a family of distributions. So you have that interpretation as well, which could be useful. So what are the situations where people actually today are using these risk measures? It turns out in the context of fairness, that's been an important area. And why? Well, when it comes to fairness, we're really focusing on safeguarding us having high average losses for some groups, but much less for other groups. Because fairness is about having, somehow equality in some sense across many groups. So if I look at the average loss for each subgroup, they could vary a lot if I train in a classical way. But if I use a super quantile risk measure, what would that do? It will really squish down those groups or reduce the loss values for those groups that have very high loss values, because the risk measure puts focus on those guys that are somehow extra bad in a much more aggressive way than an expectation would do. Of course, in classical set, we just have expectation, but now we have the flexibility, and you can, be as risk averse as you want by adjusting alpha. I have a little bit more details about that on this slide, but I think that's all good. Maybe can I show you one last picture, and that is we can even take this into classical regression. All of you know about least square regression. That is, of course, that red line that goes straight through the data cloud. This is the first thing you learn in regression class, is how you get the least square regression. Least square regression, from my point of view, is to minimize expectation. Okay. So it's kind of like a risk neutral way of thinking about errors. But we can do other way of quantifying error. I talked about that whole quadrangle of possibilities. I can look at quantile regression, or I can look at even super quantile regression, meaning that I'm changing the loss function that I'm dealing with. Instead of focusing on averages, I'm focusing on something more conservative. I know that quantiles, here I look at the 0.6 quantiles, it's a little bit above the median. That gets me the blue lines. I'm moving a little bit up. Keep in mind, up is bad for me, so I'm trying to be more conservative. And the super quantiles go even further up. That's the green line. So depending on how conservative you want, you might want to choose different type of regression techniques that come out that just changing different type of risk measures. Okay, so that's all. Much of this is in this survey article here that has many references, more than 300 references you can take a look at. A much more comprehensive description is in our book with one of your colleagues here in the math department, actually, Royset. And then here are some of these other references that I mentioned earlier. Thank you very much.
We have some time for questions.
So I'll ask one quick question. Thank you for a great talk. Yeah, so in slide 22, someone getting your intuition, slide 22. So you made a very interesting connection, the example, to the conditional value of risk. So you say you have $100, you take $50 and put in risk-free asset. So this new objective function is the conditional value of risk. So intuitively, the second term is a risk. The first term actually is risk-free.
Yeah, this is the problem with the word risk. You know, everybody has a different way of thinking about risk, and you even have this fundamental risk neutral versus risk averse.
Right.
So I think whenever you take the word risk in your mouth, be a little bit careful, because expect, probably the different people have different opinions about it, or like what does it mean? You're right that $50 I put in here, it was in a risk neutral investment in a way, but I think their risk is used in a slightly different way that my big risk in this talk, but risk-free investment, risk neutral investment, things like that. I guess that's important in finance, but I think I'm using risk in a little bit more broader sense here. But it's fine.
It does impact the second term though, the couple.
Yes. So the second term, I call that the kind of the displeasure that I feel if I face a particular random variable in the future and I have those $50 in the pocket or in the bank. So I think about that as a displeasure, more like a utility, expected utility type of thing. But there are different ways to interpret it.
Thank you so much.
Well, question back there.
Thank you very much for all of this. Do you know if this has been applied for cost-benefit analysis, like formally or by some?
I can't give you a particular reference, but I suspect, I guess cost-benefit analysis is a big topic. I mean, it's being used in so many different areas, but I think this would be a great tool in that context because, cost-benefit, that's the important trade-off, but both the cost and benefits are uncertain. So to me, this will be, I have a cost random variable, I have a benefit random variable, and somehow I will look at the difference between those two random variables and I worry about, the variability in that difference. And in particular, variability one way, maybe I worry about costs being extra high or benefit being extra low or something like that. and I will maybe pull out a risk measure to try to quantify, in one number, what that difference random variable is, So I think that would be great, I think, but I suspect maybe some people have thought about that, but how systematically that, I don't know.
Go ahead.
So going back to your machine learning example of the loss function.
Yeah.
So instead of just using the L2 metric, for example, and if you use a super quantile, what is it doing? Because your data is your data, right? And you have given data and coming from somewhere, and what does it tell you whether you use the standard least squares or super quantile?
Well, we have two things to play with here. So, and to some extent they are related. In my setup here, it looks like we have two things. I had to choose by loss function, which is a deterministic function. It could be least squares, it could be absolute values, it could be entropy or many things. And then after I settled that, now I'm somehow, for every outcome, I'm producing a number, and I'm somehow looking at this range of numbers I'm getting due to randomness across my data. And that's where I use the risk measure. So if I have least square, for instance, here, now I have, think about plotting the residuals that we do in regression. You put in the residuals, and some are big, some are small. And what a risk measure says, particularly if that's like a super quantile, like way out there, I will say I will put all my focus on those worst residuals, the highest residuals.
So you penalize it somehow.
I will penalize them more. I will try to bring the average of the 10 highest residuals, try to bring them down. And of course, with them, all the other ones that come with them. Of course, if I replace it with an expectation, I will look at the average residual and try to bring the average down, which might cause some of those high ones to remain high.
Because it's reminded of, when people use like the algorithms right now, when they use like a weighted measure for reducing the loss.
Yeah.
So it's sort of like that.
Exactly. So if I do, weighted regression, typically you a priori, let's say this data point I'm going to give weight 50, this data point weight 10, etc., etc. So I have to decide a priori which data point to focus on. Here, this is happening adaptively. The one that turned out to be very high will be brought down, but I have to a priori have to make any choice which data point is more critical, but it happens more adaptively, I guess.
I think there are methods now that they use basically they use like weights which are not known.
Yeah.
And they use like descent methods like standard stochastic gradient descent for the parameters, but then for the weights they use a gradient ascent method. So it then becomes larger weights are penalized.
Exactly. So that, there are papers called like learn to train or train to learn, or some things like that, exactly where you, even the top layer of the neural network and some of the additional parts of the neural network that determine exactly what weight or probability should be assigned to each data point. So that could somehow be part of the training process. So exactly, so that has definitely connection with the question is, you have a clean interpretation of it, of that, what's going on in that case. Well, it's very data driven in that case. Here, I think we have a clean interpretation of what's going on. Take the average or the worst, but
so this gives a good rationale for those methods. Probably.
Exactly, it could be a rationale. I'm sure there's overlap in some way. So I think that's a good observation. Yeah, I think big connections there. I think So another question. Yeah, you go first.
Oh, okay. Yeah, I was really glad that you showed us the last slide where the definition of quality of fitting could vary. Because there was a paper that I had to argue very hard with the reviewers. The paper was on estimation. And there I talked about different risk preferences could be actually incorporated in the loss function. And then there were actually quite several reviewers say, oh, this is not even decision making. This is an estimation problem. Why are you talking about the risk preferences, right? So I had to explain, even for estimation problem, it is a decision making because you have to come up with what is good and what is not good, right?
Yeah.
So based on your experience talking to different communities who have comfort ways of thinking, I guess, or traditional ways of thinking or conceptualizing certain problem, how are things connected nowadays? You know, the statistics, the optimization, and then seeing this data analytics as like a large picture or integrated.
Yeah, I think more and more people see all these type of connections now, and I think one thing that mathematicians are good at, and here Rockefeller in particular, he's been a pioneer in this area. Is to see that actually a lot of these different efforts are connected. So whether you are trying to minimize the cost of designing a transportation system, or you're trying to minimize the loss associated with a neural network, these are very different problems, but conceptually, from a decision-making point of view in a most general sense, they're very similar. I think that's what you alluded to, and I think what all these theories said, that these kind of all fit together in a bigger picture. The tools that might have been developed in finance, but now we can use it in machine learning. And in finance, we talked about risk of losing money or something like that, but in machine learning, the risk has to do with making a bad prediction, but mathematically it's very similar. So I think that's what it's great research opportunities to kind of see, well, if it's in a bigger picture, we can use tools from this and that area. And disappointed here, reviewers don't always see this bigger picture, but I guess eventually they will. I think definitely don't necessarily think about decision-making, only decision-making, the governor sits and makes decisions. Decision-making, machine learning is in a way decision-making to pick the right neural network process. So I think the big connections and computational benefits that comes from that type of insight, yeah.
Thanks.
That was a great lecture. Thanks. I guess I was thinking about this in relation to system resilience, and I guess specifically network resilience. But there's a concept that if you want to attack a network, the way to do it is to attack the most valent or most central nodes first, so you can reduce functionality. And then the corollary of that is that a more resilient network is one where it's more balanced, right? Like you don't have very high valent, very low valent nodes. But if you're trying to explain to someone who's not a technical person and you have a quantile function that's defined by alpha, right? How do you explain to them why you chose the alpha you chose? Because I think depending on what alpha you choose, right, if you're focusing on a subset of a system that is like most at risk or most vulnerable, most damaging if it's taken down, then I think the governor might ask why 10%. Like why did you pick that number?
Yeah, but I will never go up here and show you the result only for 10%.
Okay.
I will give that curve, which has 5, 10, 15, 20, 20, 30. I would say, Mr. Governor, okay, now where do you want to be on this curve? Because it's going to be trade-offs, because the risk, as you become more risk averse, as alpha goes to 1, become more and more conservative, and go further out in there. But then there's the other side where the cost goes up. Another question is, there will be fundamental trade-offs that maybe is above our pay grade. But what we have now a tool in a relatively easy way, say, hey, we can now slide between risk neutral and risk averse the whole way. And we can say, hey, where do you want to be? Well, that's probably even, we should vote on that, because that's a big decision, how risk averse we want to be in various settings and what's the cost associated with that. So I think there's no easy answer to that.
Okay.
But now we have a way to kind of slide, and explore that dimension.
So you don't have sort of a fundamental opinion on the idea of should we be optimizing around overall system performance in a very broad scale, or minimizing risks from sort of the most vulnerable or most costly events? Or you're just saying this tool is a way that you can evaluate that trade-off?
I think one has to evaluate, because I think nobody can have the universal answer, because it depends on the setting and things like that. But I don't think anybody would have. I mean, if somebody told her they had the magic answer to that, I think they were bluffing you, because I think it's too high level of a question. It depends on the setting. Sometimes one would like to be risky. You know, you go to Las Vegas, you don't go to Las Vegas with an alpha equal to 0.9, because then you will not even walk in the door, right? So I mean, in Las Vegas, you will sometimes, you know, be risk seeking. So sometimes you will even, in my language here, go to a negative alpha to some extent, right? So they depend on the circumstances and you know, some decisions, you know, but the most important, I think, what we as engineers is that we provide the analysis and the tools that will help us to quantify some of these trade-offs.
And I remember, Professor Wetz used to give this very interesting example. Even with someone who comes to tell you that I have a clear mind of what the reliability or what the risk preference I have, after seeing the cost, the trade-off might change the idea. Because he was telling us how a CEO says, oh, we definitely want more than 90%, 98% of reliability. And then after showing, okay, yeah, for the last 2% of the better reliability, you have to pay this much. And the CEO would actually back up, say, maybe that's not what we want.
Yeah. Sure.
Are there questions from online? No. Any other questions? Okay, all right. Thank you so much.